Hello Physics 42 students. In this video, we will discuss sample problems on capacitors and dielectrics. The first problem is this. A parallel plate capacitor consists of two metal plates, as shown in the figure, each of area A equal to 150 centimeters squared, separated by a vacuum gap D is equal to 0.6 centimeter thick. What is the capacitance of this device? And what is the potential difference between the plates if the capacitor is to hold a charge of magnitude Q equal to 1 times 10 to the minus 3 microcoulomb on each plate? We are given with a parallel plate capacitor. And for a parallel plate capacitor, we can use these equations. We have C is equal to epsilon naught A divided by D. So, and also we can use this equation Q is equal to C times V later. So for the first one, we are asked to find the capacitance. Now, we are given with the value of the area, which is equal to 150 centimeters squared, and if we convert this to meters squared, this is equal to multiply this with 1 meter per 100 centimeter, and then you have to square this one, so you have 150 divided by 100 squared, that is 0.015 meters squared. So this is the area in meters squared. And then the distance between the plates is also given. It is 0.6 cm, or this is equivalent to 0.006, or 6 times 10 to the minus 3 meter. Okay, so this is the gap or the separation distance between the two plates. So we have here A over D. So we have epsilon naught multiplied by 0.015 meters squared divided by 6 times 10 to the minus 3 meter. The value of your epsilon naught is 8.85 times 10 to the minus 12. So multiplying this, we will get 2.2125 times 10 to the minus 11 farad. Okay, and then the next one is to find the voltage or the potential difference between the plates. So in order to find the potential difference between the plate, we need to use this equation. So from this equation, we can have V is equal to Q over the capacitance. So we are given with a charge. The charge that the capacitor should hold is equal to 1 times 10 to the minus 3 microcoulomb. So this means that this is equal to 1 times 10 to the power of negative 9 coulomb. Okay, so you have 1 times 10 to the power of negative 9 coulomb divided by the capacitance, which is 2.2125 times 10 to the negative 11 farad. So the potential is equal to 45.2 volts. Okay, so dividing this, we will get 45.2 volts. So take note of the unit. Coulombs per farad is actually equal to volts also. Okay, so this is the capacitance, and then this is the potential difference between the plates. Okay, Now let's proceed to the next problem. A 50-meter length of coaxial cable has an inner conductor that has diameter of 2.58 millimeter and carries a charge of 8.1 microcoulomb. The surrounding conductor has an inner diameter of 7.27 millimeter and a charge of negative 8.1 microcoulomb. What is the capacitance of this cable, and what is the potential difference between the two conductors, assuming that the region between the conductor is air? For this, we are given with the following. We are given with the charge Q, which is equal to 8.1 times 10 to the minus 6 farad. So it can be positive in the positive side, or the positive conductor, negative in the negative conductor in the outer cylinder. And then you have the diameter of the inner cylinder. We can denote it as d sub I, which is equal to 2.58 millimeter. And then the diameter also of the outer cylinder, which is equal to 7.27 millimeter. And then the length of the cylinder is also given, which is equal to 50 meter. Alright, so the equations that we will be using are the following. So we can use the capacitance for a cylindrical capacitor is equal to 2 pi epsilon naught multiplied by the length divided by ln of the radius of the outer cylinder over the radius of the inner cylinder. And also, we will be using our equation for the potential difference, which is Q over C, as obtained in the previous problem. So let us solve for the capacitance. Now, okay, take note that we are given with the diameter of the inner and the outer cylinder. But in the equation, we should use radius. However, it would be okay for us to use the values of the diameter instead of the radius, because this is division, or if we take the ratio of the outer radius and the inner radius, it is the same as if we take the ratio of the outer diameter and the inner diameter. Okay, so you have we can use these values as is. So we have C is equal to 2 pi epsilon naught multiplied by the length, which is 50 meter, divided by ln of d outer over d inner. So 2 pi epsilon naught multiplied by 50 divided by ln of 7.27 millimeters divided by 2.58 millimeters. Okay, so this is equal to 2.68 times 10 to the negative 9 farad, or this is equivalent to 2.68 nanofarad. Alright, so this is the capacitance. And then to find the potential difference between the plates or between the cylinder, then we have this one, V is equal to Q divided by C. Now we are given with Q, which is 8.1 times 10 to the minus 6 coulomb. And then the capacitance, we have obtained it. So you have 2.68 times 10 to the minus 9 farad. So this is equivalent to 3018 volt. So this is the voltage difference, or the potential difference between the two conductors in our cylindrical capacitor. And then for the next problem, we have 4 capacitors connected as shown in the figure. So find the equivalent capacitance between points A and B. So this is point A and point B. And calculate the charge on each capacitor if the potential difference between point A and point B is equal to 15 volts. Okay, so we are given with 4 capacitors, 15 microfarad, 3 microfarad, 6 microfarad, and then we have 20 microfarad capacitors. Now, recall that for capacitors in series, we have 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. So you can get the capacitance of the equivalent capacitance. You can get the equivalent capacitance of capacitors that are connected in series using this equation. And then for capacitors in parallel, we have C equivalent, or the equivalent capacitance is equal to C1 plus C2 plus C3 and so on. Let us identify how are these capacitors connected. Okay, so from here we can see that the 15 microfarad capacitor is in series with the 3 microfarad capacitor, and they are in parallel with the 6 microfarad capacitor. And all of these capacitors are in series with the 20 microfarad capacitor. Okay, so let us get the equivalent capacitance for these capacitors, this network of capacitors. Okay, so let us start with the 15 and the 3 microfarad capacitors. Suppose we can call this C1, C2, C3, and then C4. First is to find the equivalent capacitance here. So the 15 microfarad capacitor is in series with the 3 microfarad capacitor. So you have 1 over C12 is equal to 1 over C1 plus 1 over C2. So this is equal to 1 over 15 microfarad plus 1 over 3 microfarad. Okay, so if you add this two, you will get 2/5. Take note that the unit of this is per microfarad. Okay, so C12 or the equivalent capacitance of these capacitors is equal to C12, and it is equal to the reciprocal of 1 over C12. So you have 1 divided by 2 over 5. So you have 5 over 2 microfarad, or this is equal to 2.5 microfarad. Okay, so this is the equivalent capacitance of these two capacitors. Now, C12 is in parallel with C3. Okay, so C12 is connected in parallel with C3. So, kini sila, pwede ni siya nato ilisan og isa ka capacitor that has an equivalent capacitance equal to 2.5 microfarad. And this kato siyang 2.5 microfarad capacitor is in parallel with C3. So, we have C123 is equal to C12 plus C3 because they are in parallel. Your C12 is 2.5 microfarad, and then your C3 is 6 microfarad. So your C123 is equal to 8.5 microfarad. Okay, so we have obtained an equivalent capacitance of these three capacitors. And kung isahon ni siya nato, ang iyang equivalent capacitance is C123, which is 8.5 microfarad. And C123 is connected in series with C4. Therefore, 1 over C equivalent is equal to 1 over C123 plus 1 over C4. So your C123 is 8.5 microfarad, and your C4 is 20 microfarad. So this is equivalent to 57 over 340. The unit is per microfarad or microfarad inverso. Okay. Or 57 over 340 per microfarad. Okay. So your C equivalent is equal to the reciprocal of this value, which is equal to 340 over 57. The unit is microfarad, or this is equivalent to 5.96 microfarad. Okay, so this is the equivalent capacitance. And this is what we are looking for. Okay, and then for letter B, we are asked to calculate the charge on each capacitor if the voltage difference between the two points A and B is equal to 15 volts. Okay, so given VAB is equal to 15 volts, and then we have obtained also the equivalent capacitance, which is 5.96 microfarad. Okay, now we can get the total charge that is in our circuit. So the total charge, Q total, can be obtained by multiplying the equivalent capacitance and the potential difference between A and B. So you have 5.96 microfarad multiplied by 15 volts. So since we have microfarad and volts, we will get microcoulomb. Okay, so this is equivalent to 89.4 microcoulomb. So this is the total charge that is flowing through the circuit. Now we know that for capacitors that are connected in series, the charge is constant. Therefore, if C4 is in series with C123, then C4 will have a charge equal to 89.4 microcoulomb. Since C4 and C123 are connected in series, then Q4, the charge on capacitor 4, is equal to 89.4 microcoulomb, and it is also equal to the charge on C123. Okay, so you have Q123 is also equal to 89.4 microcoulomb. Now that we have Q4, we will then get V4. So we can get V4. So V4 is equal to Q4 divided by C4. So your Q4 is 89.4 microcoulomb, and then your C4 is 20 microfarad. So you have 4.47 volts. Okay, so the voltage drop across capacitor 4 is equal to 4.47 volts. Since C4 and C123 are connected in series, then your VAB should be equal to V123 plus V4. Okay, so when we add the voltage drop across C123 and C4, we will get the voltage across point A and B. And we know that this is 15 volts. This one is 4.47 volts. Therefore, V123 is equal to VAB minus V4. So you have 15 volts minus 4.47 volts. So this is equal to 10.53 volts. Okay, so the voltage drop across capacitor 123 is equal to 10.53 volts. So now we will use this information to find the charges in each capacitors. Okay, so recall ang ato ang gipangita is or the charge on each capacitor. So Ang ato palang nakuha is the charge on capacitor 4, and it is equal to 89.4 microcoulomb. Okay? So, kini pa lang so far ang atong nakuha. Now, we will get Q3, Q1, and Q2. Okay? So, we will be using our information that diri ang voltage drop diri V4 is equal to 4.47. And since it is in series with this 3, when we replace this with a single capacitor that has an equivalent capacitance C123, then ang iyang voltage is equal to 15 volts minus 4.47, or it is equal to 10.53 volts. Now, what we know also is that your C12 is in parallel with C3. So, if the voltage drop across C123 is 10.53 volts, then it must be that the voltage across capacitor 3 is also equal to 10.53 volts. So this is also 10.53 volts since they are in parallel with C12. Therefore, since C3 is in parallel or is connected in parallel with C12, then V3 is equal to V12, which is equal to V123, which is equal to 10.53 volts. Okay, now that we have V3 equal to 10.53 volts, we can then get Q3. So Q3 is equal to C3 multiplied by V3. So your C3 is 6 microfarad multiplied by your voltage, which is 10.53 volts. So we get 63.18 microcoulomb. So take note of the unit. It's microfarad multiplied by volts, so you will get microcoulomb. 63.18 microcoulomb. So this is our Q3. So far we have obtained Q4. We have obtained Q3 also, which is equal to 63.18 microcoulomb. Now, we know that V12 is also equal to 10.53 volts. Therefore, V12 is equal to 10.53 volts. We can get Q12. So Q12 is the charge that is stored in capacitor C12. So Q12 is equal to C12 multiplied by V12. So recall that C12 is equal to 2.5 microfarad. So the equivalent capacitance of these two capacitors is equal to C12, which is 2.5 microfarad. So you have 2.5 microfarad multiplied by the voltage, 10.53 volts. This is equal to 26.325 microcoulomb. Okay, so this is your Q12. Now, take note that for capacitors in series, the charge is the same. If the charge on C12 is equal to 26.325 microcoulomb, take note that C1 is in series with C2. Therefore, parehan ni sila og charge diri a. Okay, so Q1, we can say that Q1 is equal to Q2 and is equal to Q12, which is 26.325 microcoulomb. Okay, so now we have obtained the charges in each of the four capacitors. So we have Q1 is equal to Q2, which is equal to 26.325 microcoulomb. Q3 is 63.18 microcoulomb. And then Q4 is 89.4 microcoulomb. Now let us check this. The total charge of these three capacitors should be 89.4 microcoulomb, the same as this one. Okay, so you have your Q1 and Q2 have the same charge. They are in series. So Q1, 2, 3 is equal to, we know that Q123 is equal to 89.4 microcoulomb. Let us see if Q123, this is equal to Q12 plus Q3. Q12 has a charge of 26.325 microcoulomb, and then your Q3 has a charge of 63.18 microcoulomb. Okay, so this is for checking purposes. Alright, so your Q123 is equal to 89.505 microcoulomb. Okay, so from here, we have Q12 plus Q3 is equal to 26.325 plus 63.18 microcoulomb, which is equal to 89.505 microcoulomb, which is almost the same, or which is just the same as your Q123. So these answers are correct. Now let us move on to the next problem. We have another network of capacitors. Each capacitance C1 is equal to 6.9 microfarad and each capacitance C2 is 4.6 microfarad. Compute the equivalent capacitance of the network between points A and B. So for this problem, we just have to compute the equivalent capacitance of the network between point A and point B. So this is your point A, this is your point A, and this is your point B. Now, take note, class, that these three capacitors here are connected in series. Okay, so in order to get the equivalent capacitance of these capacitors, it is like replacing it with a single capacitor that has an equivalent capacitance of this network. Okay, so take note that for this problem, we need to start at the farthest end, or dirita magsugod. Okay, so suppose this is your capacitor 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 capacitors and we will start with this. So capacitors 1, 2, 3 are in series, and their equivalent capacitor is in parallel with this. Okay, so let us label this one first para dito maglibog. 1. This one is capacitor 2, capacitor 3, 4, 5, 6. This is 7, 8, and capacitor 9. Capacitors 1, 2, 3 are in series with each other. So let us write this one. So again, you have to start with the farthest from point A. So capacitors 1, 2, and 3 are in series with each other. Therefore, 1 over C123 is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So we have your C1, 2, 3 are all C1s. So you have 6.9 microfarad. You have 3 multiplied by 1 over 6.9 microfarad. So you have 3 over 6.9 microfarad. Or your C123 is equal to 6.9 over 3 microfarad. So you will get 2.3. Okay, it's 2.3 microfarad. You now have a single capacitor replacing these 3 capacitors. Okay, so the equivalent capacitance of these 3 capacitors is 2.3 microfarad, and it is in parallel with this 4th capacitor. Okay, so it is in parallel with the 4th capacitor. So if we draw that one, so this is point A, point B, you have capacitor here, capacitor 9 and 8 here, capacitor 7, this one, capacitor 5, capacitor 6, and then you have capacitor 4. Now, the 3 capacitors will be replaced with a single capacitor that has a capacitance equal to C123. Okay, so yung ano na siya. Now, your C123 is parallel with C4. Therefore, take a look at this drawing, class. C123 is parallel with C4. Therefore, C123 is parallel with C4. Therefore, C1234 is equal to C123 plus C4. So, you have your C123 is 2.3 microfarad plus your C4 is 4.6 microfarad. 4.6 microfarad. So you have 6.9 microfarad. Your C1234 is equal to 6.9 microfarad. And then after this, kini siya nga drawing will become something like this. Okay, so this is the 8th and the 9th capacitor. The 7th capacitor. This one is the 5th capacitor, the 6th capacitor. And then, kini siya diri, this will become your C1234. Okay, so, na-simplify na siya no, from this very complicated network to this. So, this is 1, 2, and then 3. Okay, so now you can see that C5 is in series with C1234 and C6. Therefore, you have 1 over C123456 is equal to 1 over C1234 plus 1 over C5 plus 1 over C6. Okay? So, C1234, C5, and C6 are connected in series. Therefore, you can get the equivalent capacitance using this equation. So, you have 1 over C123456 is equal to 1 over 6.9. This one also is your C5 is C1. Your C6 is equal to C1, which is 6.9 microfarad. Therefore, you will just multiply this with 3. Okay, so this is equal to 3 divided by 6.9 microfarad. Therefore, your C123456 is equal to 2.3 microfarad. Okay. So we have obtained C1234. We have also obtained C123456. So, kini siya diri maisa na lang po ni class, no? This will become something like this. You have, so this is your C123456. Okay? So, kining tulo ka capacitors diri, giilisa na po nato another single capacitor with capacitance equal to C123456. Now, take note that it is in parallel. It is connected in parallel with C7. So, pwede na po na ito makuha ang C123456 Okay? C123456 is in parallel with C7. Therefore, C123456 is equal to C123456 plus C7. You have 2.3 microfarad, and then your C7 is equal to C2, which is 4.6 microfarad. So you have plus 4.6 microfarad, and we will get 6.9 microfarad. So this two, C123456 equals 6.9 microfarad. So you have this one. Yan na dayon. Pwede na siya nato makuha ang equivalent capacitance. So this is point A, this is point B. Okay. And then this is your C123456 Now, they are connected in series. These three capacitors, C8 o C9, are connected in series. Therefore, our equivalent capacitance, C1, 2, 3, 4, 5, 6, 7, C8, and C9 are connected in series. Therefore, 1 over C1, 2, 3, 4, 5, 6, 7, 8, 9, which is, getting C1, 2, 3, 4, 5, 6, 7, 8, 9 is your equivalent capacitance. So this is equal to 1 over C1, 2, 3, 4, 5, 6, 7 plus 1 over C8 plus 1 over C9. And these are all 6.9 microfarad. So you have 3 multiplied by 6.9 microfarad. Or you have C equivalent is equal to 2.3 microfarad. Okay? So the same as this. 3 over 6.9 microfarad. So your C equivalent is equal to 2.3 microfarad. So for our next problem, we have this network of capacitors. So in the figure, C1 equal to C5 is equal to 8.4 microfarad, and C2, C3, and C4 is equal to 4.2 microfarad. The applied potential is equal to 220 volts. What is the equivalent capacitance of the network? And calculate the charge on each capacitor and the potential difference across each capacitor. So we have 5 capacitors, C1 to C5, and we are given with the capacitances as well as the voltage applied between point A and B. So we are asked to find the equivalent capacitance. So we will start with the farthest from the potential from this point A and B. So we will start with C3 and C4. So C3 and C4 are in series with each other, are connected in series. Therefore, 1 over C34 is equal to 1 over C3 plus 1 over C4 is equal to 1 over 4.2 microfarad. And C4 is also 4.2 microfarad. So we have 2 multiplied by 4.2 microfarad. So we have 2 over 4.2 per microfarad. So our C34 is equal to the reciprocal of this one, which is 4.2 over 2 microfarad. So we have 2.1 microfarad. So this is the equivalent capacitance of C3 and C4. Now, C34 is connected in parallel with C2. Therefore, C234 is equal to C2 plus C34. So you have C2 is 4.2 microfarad plus C34 is 2.1 microfarad. So we have C234 is equal to 6.3 microfarad. So we have the equivalent capacitance for C3, C4, and C2. Now, our network of capacitors have become this one. So this is your C1, this is C5, and then this is your C234. So this is C234. Now, as you can see, they are all in series with each other. They are connected in series with each other. So we have C1, C2, 3, 4, and C5 are in series. Therefore, 1 over C1, 2, 3, 4, 5, or this is your C equivalent. C1, 2, 3, 4, 5 is your C equivalent. 1 over C equivalent is equal to 1 over C1 plus 1 over C2, 3, 4 plus 1 over C5. So you have 1 over your C1 is 8.4 microfarad, 8.4 microfarad plus your C234 is 6.3 microfarad, and then your C5 is also 8.4 microfarad. So you will get 10 over 23 per microfarad, or your C equivalent is equal to 23 over 10 microfarad, or this is equal to 2.3 microfarad. Okay, so this is our equivalent capacitance of the 5 capacitors. Now, next is to find the VIs and the QIs. Okay, so the next thing that we will do is to find the VIs, meaning to say V1, V2, V3, V4, and V5, and also the QIs, the charge on each capacitor. Okay, so we are given with VAB, which is equal to 220 volts. So we can get the Q total. Q total is equal to C equivalent multiplied by VAB. So this is equal to 2.3 microfarad multiplied by the voltage, which is 220 volts. So we get 554.4 microcoulomb. Okay, so this is the total charge that is in the circuit. We know that Q1, so from our figure, C1, C5, and C234 are connected in series. So if the total charge that is flowing in the circuit is equal to 554.4 microcoulomb, then it is also the charge that is flowing on capacitor 1. So Q1 is equal to 554.4 microcoulomb also. The same with your Q5. Your Q5 is also 554.4 microcoulomb. And also your Q234, or the charge that is flowing through C234, is equal to 554.4 microcoulomb. Okay, so from here we can say that Q1 is equal to Q5, which is equal to Q234, which is equal to the Q total. Our Q total is equal to 554.4 microcoulomb. Okay? Since these three capacitances are in series with each other, their charge are the same. Now, from here, we can get the voltage drop across C1 and C5. So V1 is equal to Q1 over C1. So your Q1 is equal to 554.4 microcoulomb. And then your C1 is 8.4 microfarad. 8.4 microfarad. So your V1 is equal to 66 volt. Your V5 is equal to Q5 divided by C5. So this is also equal to 554.4 microcoulomb. And then your C5 is also equal to 8.4 microfarad. Therefore, the voltage drop across capacitor 1 and capacitor 5 are both 66 volt. Okay, we can also get the voltage drop across C234, and it is equal to Q234 divided by C234. And we have obtained Q234 to be equal to 554.4 microcoulomb. And our C234 from the previous slide, C234 is equal to 6.3 microfarad. Therefore, your V234 is equal to 88 volt. Now, when you add these three, it should be equal to 220 volts. So 66 plus 66 plus 88 should be equal to 220 volts. Now take note, class, that since C34 is connected in parallel with C2, okay, so C34, C2, and C34 are parallel, okay? Therefore, whatever is the voltage drop on C2 is also the voltage drop on C34. Okay, so let us write. So this is also the voltage drop across C2 and C34. Okay, so therefore V2 has a voltage drop, or C2, capacitor C2 has a voltage drop V2 which is equal to 88 volts. And this is also equal to the voltage drop across V34, across C34. So this is also equal to 88 volts. Now that we have obtained V2, we can get Q. So Q2 is equal to C2 multiplied by V2. So your C2 is equal to 4.2 microfarad, and then your V2 is equal to 88 volts. Therefore, your Q2 is equal to 369.6 microcoulomb. Okay. So far we have obtained Q1, Q2, and Q5. And also, we have obtained V1 and V5 and V2. Okay, so what is left to find is V3 and V4, Q3 and Q4. So Q2 is equal to 369.6 microcoulomb. Now, we also know that V34 is equal to 88 volts. So, we can get Q34. So, Q34 is equal to C34 multiplied by V34. So, this is equal to your C34 is 2.1 microfarad. And then your V34 is equal to 88 volts. So when we multiply this, we will get Q34, and it is equal to 184.8 microcoulomb. So this is your Q34. Now take note that C3 and C4 are in series with each other. So therefore, if the charge across C34 is 184.8 microcoulomb, then the charge on C3 is also 184.8 microcoulomb, and also the charge on C4. Okay, so since they are connected in series, we can say that since C3 and C4 are in series, then Q3 is equal to Q4 and it is equal to Q34. So this is 184.8 microcoulomb. Alright, so we have obtained all the charges on each capacitors. Now, what is left to find is the voltage across C3 and C4. So V3 is equal to Q3 over C3. So you have Q3 is 184.8 microcoulomb divided by 4.2 microfarad. 4.2 microfarad. So your V3 is equal to 44 volts. Okay, so V3 is equal to 44 volts. And then here V4 is equal to Q4 over C4. So your Q4 is also 184.8 microcoulomb. And then your C4 is equal to 4.2 microfarad. Therefore, your V4 is equal to 44 volts also. Okay, so now we have obtained all the charge in each capacitor and all the potential difference across each capacitor. Okay, so for the next problem, an air-filled parallel plate capacitor has a capacitance of 5 picofarad. A potential of 100 volts is applied across the plates, which are 1 centimeter apart, using a storage battery. What is the energy stored in the capacitor? Suppose that the battery is disconnected and the plates are moved until they are 2 centimeters apart. What now is the energy stored in the capacitor? And suppose instead that the battery is left connected and the plates are again moved until they are 2 centimeters apart. What is the energy stored in the capacitor in this case? Okay, so for this problem, we are given with the following. We have C is equal to 5 times 10 to the minus 12 farad. So this is picofarad. So we are given with 5 picofarad. So this is equivalent to 5 times 10 to the minus 12 farad. And then the voltage difference, the potential difference is equal to 100 volts. And then the separation distance between the plates is equal to 1 times 10 to the minus 2 meter. 1 centimeter or 1 times 10 to the minus 2 meter. And then what we know, so what are the useful equations for this problem? So we have U is equal to 1/2 CV squared, and then U is equal to Q squared over 2C. Okay, so the first thing that we will calculate is the energy stored in the capacitor. So in order to solve for the energy stored in the capacitor given the capacitance and the voltage, we can use this equation. So U is equal to 1/2 multiplied by CV squared. So you have 1/2 multiplied by 5 times 10 to the minus 12 farad multiplied by the voltage, which is 100 volts. So we get 2.5 times 10 to the minus 8 joules. And then for letter B, we are asked to calculate the energy stored in the capacitor if the battery is disconnected and the plates are moved until they are 2 centimeters apart. Okay, so for this, D is doubled. Okay, so for this problem, D is doubled. It has become 2 centimeters. So when D is doubled, the capacitance is halved. So the new capacitance will be, instead of 5 times 10 to the minus 12 farad, so it will become 2.5 times 10 to the minus 12 farad. Okay, so this is the new capacitance. Now, the battery is disconnected. So as the plates are separated farther from 1 centimeter to 2 centimeters, the battery is disconnected. So this means that the charge is constant. So changing the separation distance between the plates while disconnecting the battery, this means that Q is constant. Okay, so we will be using this equation. So if Q is constant, then we will use this equation. U is equal to Q squared over 2C, the new C. So you have, we can write C prime. So this is your C prime, the new C. So you have Q squared over 2 multiplied by your C1. Your C1 is 1/2 of the original C. So you have C over 2. So your C prime is equal to C over 2. So you have Q squared over 2C multiplied by 2. Therefore, the potential energy is doubled. So when D is doubled, your C is halved, and when the battery is disconnected, Q is constant. Therefore, your U will be doubled. So twice that of our original, so this is U prime, twice that of our original U. So 2 times U, which is 2 times 2.5 times 10 to the negative 8 joules. So you have 5 times 10 to the minus 8 joules. Okay, so this is the new stored potential energy when the separation distance between the plates is doubled and the battery is disconnected. Okay, so your electric potential energy stored in the capacitor is doubled. And then for letter C, suppose instead of the battery is left connected and the plates are again moved until they are 2 centimeters apart. What is the energy stored in the capacitor in this case? Now, if the battery is left connected, this means that the voltage is constant. Okay? The process takes place at constant voltage. Therefore, our U prime constant voltage. So take note that if the battery is left connected while the conductors are separated to 2 centimeters, the voltage is constant during the process. So we have U is equal to, or U prime is equal to C prime V squared over 2. So the same raghapon class, since the separation distance is doubled, your C is halved. Okay? So therefore, this is C over 2 multiplied by V squared divided by 2. Or this is equal to 1/2 multiplied by CV squared over 2. Therefore, your U prime is equal to 1/2 of the original, 1/2 of the original 2.5 times 10 to the minus 8 joules. So this is equal to 1.25 times 10 to the minus 8 joules. Alright, so take note of the difference. Okay, so when you change the property of the capacitor by changing the separation distance between the plate, magmatter ay kung nakakonect ba or disconnected ang battery during that process. So if the battery is disconnected, Q is constant and the potential energy stored will be doubled. And if the battery is connected during the process, the potential energy will be halved. So we have another problem. This will be the last problem that we will be solving. So for the last problem, we have a parallel plate capacitor of area 2000 centimeters squared or 1 centimeter apart. The capacitor is connected to a power supply and charged to a potential difference V naught equals 3000 volts. It is then disconnected from the power supply and a sheet of insulating plastic material is inserted between the plates, completely filling the space between them. We find that the potential difference decreases by 1000 volts while the charge remains constant. Compute the original capacitance C naught, the magnitude of charge Q in each plate, the capacitance C after the dielectric is inserted, the dielectric constant K of the dielectric, the permittivity of the dielectric, epsilon of the dielectric, and the magnitude of the induced charge Qi on each face of the dielectric, and the original electric energy, electric field between the plates and the electric field after the dielectric is inserted. Okay, so let us start with the given. So what are the given? So we are given with the area of the plate, which is 2000 centimeters squared. So if we convert this to meters squared, this is equal to 0.2 meters squared. And then the separation distance is 1 cm. So this is equal to 1 times 10 to the minus 2 meter. And V naught, which is equal to 3000 volts. So for letter A, we need to find the capacitance before the dielectric is inserted. Okay, so we have this equation. The area is 0.2 meters squared divided by 1 times 10 to the minus 2 meter. So C naught is equal to 1.77 times 10 to the minus 10 farad. Okay, and then the charge Q. So to find the charge Q, we have Q is equal to C naught multiplied by V naught. So our C naught is 1.77 times 10 to the minus 10 farad. Multiply this with V naught, which is 3000 volts. So we get Q naught equals 5.31 times 10 to the minus 7 coulomb. So this is your Q, the charge on each plate, before the dielectric is inserted. Now, for letter C, we are to find the capacitance after the dielectric is inserted. Okay, so what we have known so far is the area of the plate and the separation distance, but we do not know what material was inserted. So we can get the capacitance of the material or the capacitor after the dielectric is inserted, noting that it is disconnected from the power supply before the sheet is inserted, the insulating sheet or the dielectric is inserted. This means that Q is constant during the process. So we have Q over V. So what we know is that the Q is equal to 5.31 times 10 to the minus 7 coulomb divided by the voltage, which is after the voltage has become 1000 volts after inserting it with the dielectric. So the new capacitance is equal to 5.31 times 10 to the minus 10 farad. Okay? So it has increased. And then for letter D, we are asked to find the dielectric constant of the material. So to find the dielectric constant, we will use this equation. So you have K is equal to C divided by C naught. So if we take the ratio of the new C, the new capacitance, by the capacitance in vacuum, then we will get the dielectric constant, K. So we have 5.31 times 10 to the negative 10 farad divided by C naught, which is 1.77 times 10 to the minus 10 farad. This is equal to 3. So the dielectric constant is a dimensionless constant that is always greater than 1. And then for letter E, we need to find the permittivity of the dielectric. So E is equal to K multiplied by epsilon naught. So 3 multiplied by epsilon naught, this is equal to 2.655 times 10 to the negative 11 coulomb squared per Newton meter squared. Okay, so this is the permittivity of the dielectric material. And then for letter F, we need to find the induced charge. So Qi. Now the first thing that we should do is to find sigma sub I. So the induced surface charge density is equal to sigma multiplied by 1 minus 1 over K. Your sigma can be obtained by dividing Q by the area. So you have Q divided by the area multiplied by 1 minus 1 over kappa, or the dielectric constant. You have 5.31 times 10 to the negative 7 coulomb divided by the area, 0.2 meters squared, multiplied by 1 minus 1 over 3. So you have 1.77 times 10 to the minus 6 coulomb per meter squared. And then to find Q sub I, so this is your sigma sub I, or the induced charge density. So to find Q sub I, you should multiply this, the induced charge density multiplied by the area. So we have 1.77 times 10 to the minus 6 coulomb per meter squared multiplied by 0.2 meters squared. So this is equal to 3.54 times 10 to the negative 7 coulomb. So this is the induced charge due to the insertion of the dielectric material. Okay, and then for letter G, we need to find the electric field before the dielectric material is inserted between the plates. So we have sigma divided by epsilon naught. So this is equal to 2.655 times 10 to the minus 6. So this is the value of your sigma. Basically, this is the value of your sigma Q over A divided by epsilon naught. So this is equal to 3 times 10 to the 5 newtons per coulomb. And lastly is the electric field after the dielectric is inserted. So the new electric field will decrease by a factor of K. So it is equal to E naught divided by K. So if E naught is equal to 3 times 10 to the 5 newtons per coulomb and K, the dielectric constant, is equal to 3, then the new electric field is equal to 1 times 10 to the 5 newtons per coulomb. So I hope you have learned something from this video. Thank you so much for watching.